Welcome back. Today we're going to talk about the 12 basic functions, and that's going to be section 1.3. And this is going to be a combo video with section 1.6 where we talk about translating those functions. So basically we're going to look at what's the parent function, meaning its basic form, and then how do we start moving it around in the coordinate plane, stretching and shrinking it, reflecting it, etc. Let's start with the identity function. This is pretty basic. It's f of x is equal to x, or y equals x. And when we sketch this graph, it's going to go through all of these points here, right? So I'm going to do my best to connect these dots here. But you're familiar with this. It's an easy one to graph. It's got a slope of 1. And so we're looking at these functions in terms of their domain and their range. And so when we look at the domain, what doesn't it cover? Is there anything that breaks it? No. So it goes negative infinity to infinity. Okay. And its range is going to be also negative infinity to infinity, right? There's nothing it doesn't touch. It goes infinitely in one direction, infinitely in the other direction. All right, the squaring function. Now, some of these titles are going to be like, well, that's just x squared. Why does that matter? That's just their title. Okay, so like that's their proper name. The squaring function is f of x is equal to x squared, or y equals x squared. And when we're drawing these graphs, the best practice is to try to get significant points and then connect the dots. So I know that 1, 1 is on there, and I know that 2, 4 is on there. All right, so 1, 2, 3, 4. So negative 2, 1, 2, 3, 4. So this is what the squaring function looks like. And so when we look at the squaring function and those sorts of things, we're trying to figure out, you know, when we start to move these things around, what are going to be the effects? Well, we obviously see that this one is symmetric, and so it's going to have different properties when we start to reflect it, but that's the type of thing, excuse me, that we're looking for. Domain, what's the domain? Well, the domain is from negative infinity to infinity, so it's all real numbers. And its range, however, is, as defined by the graph and as defined by the function, literally only goes from 0 to infinity, because we can't have a negative number. If you put in a negative for the domain and square it, it becomes positive. Cubing function. With a cubing function, it's going to go through 0, 0, so it would be 0 cubed. 1 cubed would be 1, negative 1 cubed would be negative 1. And then we start to get into this situation where we're going to run out of spaces. So 2 would be 8. So 1, 2, 3, 4, 5, 6, 7, 8, somewhere up here. And then 2, negative 8 is somewhere down here. It looks like stretched sort of an S kind of a curve here. So as far as domain is concerned, it goes from negative infinity to infinity, and then its range is also negative infinity to infinity, right? Because negatives aren't excluded in this case. Absolute value function. Absolute value function is that one that looks like a V, right? So it looks like this. And so it's going to have 0, 0. It's going to have 1, 1. It's going to have negative 1, 1. It's going to have 2, 2. It's going to have negative 2, 2. And so it looks like a V because you can't have, excuse me, you can't have a negative output here, right? Because every value is going to get popped back up into that positive part. So when we talk about domain, we've got negative infinity to infinity. But our range, again, is going to be this 0 to infinity kind of a situation. All right, reciprocal function. Reciprocal function is 1 over x, and if you remember, it kind of looks like this. It's sort of this like two-parter, and we're going to look at y. And so what we need to understand is we've got an asymptote, right, at x equals 0. Okay, so putting in an asymptote is important. So we've got an asymptote at x equals 0, and also we've got an asymptote at y equals 0. Well, why? Because you can't make it 0, right? So how would you say 0 is equal to 1 over x? Well, 0x would equal 1. There's nothing times 0 that equals 1. So you've got an asymptote there. And this graph goes like this. Okay, and so it's everything down below here and everything up above. Its domain is from negative infinity to 0, but we don't include 0 because it can't be in there, and then 0 to infinity. right? So our domain is negative infinity and 0, but excluded, and then comes down from positive infinity, but doesn't touch 0, and then keeps going into infinity. Our range is the same, so negative infinity to 0, and then 0 to infinity, because we have those asymptotes at x equals 0 and y equals 0 that keep us from being able to do this. All right, next one. Square root function goes through 0, 0. Remember we talked about that the other day. So you can take the square root of 0. It's just 0. The square root of 1 is 1. And then it would go out to the square root of 1, 2, 3, 4 is 2. So it looks like this. Square root functions always felt a little like incomplete to me. It's like, done. Okay, so with the square root function, notice what's happening here. So our domain, we can't put in a negative number, but we can put in 0. So our domain is 0 to infinity. So it's like, you know, you got this line here. You can't put in anything past 0. You put in 0 and the positive stuff, but nothing else. Our range is the same way. So we can get a 0 and we can get anything positive, but we can't get anything negative because of this the square root function. We got about 6 more, so halfway through. Exponential growth function. The exponential growth function looks like this. It's e to the x. And so e to the 0, like e to the 0 would be 1, because anything to the 0 power is 1. And our exponential growth function looks like this. Okay, exponential growth. Bacteria grow in this way. And so labeling this, putting the significant point in there is a good idea. Our domain, check it out. What's our domain? So for our domain, no restrictions here, right? You can raise e to a negative power. You can raise e to a positive power. It gets really big really quickly or really small really quickly, but you can put in anything. Our range, however, you can't get 0, right? So if I had, let's say, e to the negative 2, it would be 1 over e to the 2, right? Well, now it's a fraction. So it can't go on the bottom. 0 can't go on the bottom. And so I cannot put in a 0. 0 can't come out. So I couldn't have something go to 0. So in that way, it's sort of like that reciprocal function that we were just talking about. But our range here is 0 to infinity because we stay in the positive realm because it's still an exponent after all. It's x in the exponent. But we can't have a negative, we can't, because it's when you put a negative x in, it becomes a fraction, so you can't ever get 0. Basic logistic function. So here we've got a situation where we need to do a little bit of labeling, and our labeling is like this. So in this case, this is going to be 0.5. So this is a half. So this is actually 1 up here. And our basic logistic function looks like this. 1 over 1 plus e to the negative x. Well, so check out what happens. So since I've got a fraction, this can't equal negative 1, right? Because then it'd be 1 plus negative 1. And so because e to the negative x can't equal negative 1, it severely limits what can go in. And so my basic logistic function looks like this. Okay? It looks like a sideways S. And actually, I need to redraw this because that's not really, I'm not doing it justice. I'm trying. I'm trying to do it justice, but I'm not doing it justice. It comes all the way from infinity. And it's approaching 1, but it can't get to 1. So our domain for our basic logistic function is negative infinity to infinity. And our range is from 0 to 1. Okay, so it can't get to 1. They're not included. So it can't get to 0 because I can't have that 0. And it can't get to 1 because I can't get there because I'm raising this to this negative power. Okay, so my range is between 0 and 1. Natural logarithmic function. Looks like this. It's the natural log of x, and like I said, you can graph these. Like if you graph these, then you could end up with a case where you see for yourself exactly what's going on. I'm just explaining it to you. And so this is going to go through 1 here. So It's going to look like this. So the natural logarithmic function has a domain from 0 to infinity. Okay, so I can't put in 0, and I can't take the natural log of 0. I can't take the natural log of a negative number. And my range is negative infinity to infinity. As you observe these graphs, understand what's going on here. My range is negative infinity to infinity because it comes from negative infinity and it keeps going up into infinity. Okay, but it gets cut off. There's an asymptote right there at 0 that keeps it, so I can't have 0 in my domain. This one's a silly one. You've probably never seen this one before. The greatest integer function, which is defined as int x, int parentheses x, defines the greatest integer that is less than or equal to a number. And so as we go through here, let me show you what it looks like. This is also known as the stair-step function. And you're going to be like, what in the world? Well, we've got a bunch of like jump discontinuities here. And so these jump discontinuities tell us that, let's say I'm in the interval from 0 to 1. Okay, the greatest integer less than or equal to, let's say, 0.5 is 0. And so all of these things are 0 here. But when I get to 1, the greatest integer less than 1 is 1. All the way up until I get to 2, the greatest integer is 1. The greatest integer less than or equal to those is 1. Jumps up to 2. So between 2 and 3, so like 2.5, what's the biggest integer less than or equal to that? It's 2. And so from 2 to 2.5, my function is defined as 2, right? And so my domain is actually all real numbers, so it's negative infinity to infinity. And my range is all integers. Okay, it's not all real numbers because I can't have a range of 1.5. My range is 0, 1, 2, 3, 4, 5, 6. So it's all the integers. That's a silly one, okay? But it's the best example of jump discontinuity that we have, and it's one of those 12 basic functions that help us out. Okay, the sine function. Sine function is, it's not sin x, it's sine x. That's the definition of the function. It's sine x. And for sine x, it looks like this. And we're going to talk a little bit more about this as we go along. But to draw the sine function is to be able to look at the graph and break it into, and you're going to be like, I don't really understand that, but to break it into fractions of pi, okay? And so it's important when we get to this trig part, and this is going to keep going. I'm trying to do a really good job of connecting the dots here. Yeah, okay, perfect. You're going to be breaking it into fractions of pi, and so actually, you know, this right here is not 2 or 4 or any other integer, it's 2 pi, and this is pi here. And so this is pi over 2, meaning this is actually, it's along the x-axis here, so it's not confusing. It's actually, you're going to see what its range is in just a minute. This is actually 1 up here. But our x values are, in this case, for the parent function, our x values are going to be defined as intervals of pi. So pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, et cetera, et cetera. Back here, this is like negative pi. Got to draw. Can't drag there. Hold on. This is negative pi over 2, right? And this is negative pi. This would be negative 3 pi over 2, and this would be negative 2 pi. And so, what am I saying here? Well, I'm really not saying anything too groundbreaking right now. It'll become significant. My domain is still negative infinity to infinity. I'm just breaking up my coordinate plane, my x-axis, into slices that are not integers, which is really hard for us to comprehend sometimes. But our range is from negative 1 to 1, okay? So this down here, this is negative 1, and up here is 1, okay? So it oscillates, negative 1, 1, negative 1, 1, negative 1, 1, over the course of this sine function. cosine. You're going to be like, wow, that looks really, really familiar. Well, actually, it's the cosine function and the sine function are just like, actually, they're translations of one another. But cosine is a distinct function from the sine function. And unlike the sine function, it starts, now we're talking about the parent function here. It starts at the top. So it's going to start at 1. But it also has those same breakdowns. This is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi here, right? And so its domain is still negative infinity to infinity. It has the same range of -1 to 1, but it's just shifted over a little bit, okay? It's still its own distinct function, but it has its own domain, its own range. And so now that we have those 12 basics, just take a look at this for a second. We're going to start talking about exactly what does it mean to translate these things. We can move them up, we can move them down, left, right, stretch them, shrink them, those sorts of things. All right. When we consider the parent function x squared, okay, we're looking at one that looks like this. When I look at x squared plus 3, this is the same function, just up 3. If I was going to do x squared minus 4, this is the same function, just down 4. It works for non-integers as well. This one would be up pi. Okay? For this next one, what I'm doing is this. I'm looking at, let me pull up, a graph here for you. Because what I'm asking you to do is I'm asking you to look at the graphs here. I've got x cubed plus, these should be cubes here. Sorry about that. So these should be cubes here. What I'm asking you to do is I'm asking you to graph these and just look. Just look at how it changes. And so what I'm going to do is I am going to graph f of x is equal to x cubed to give me an idea. This is my parent function, right? This is one we just talked about. So it looks like that sideways s. And the one that I'm asking you to graph is, let me grab my sheet here so I'm flipping back and forth. Hold on. The one that I'm asking you to graph is x plus 3, so f of x is equal to x plus 3 cubed. So check out what happens. When I add 3 inside the parentheses, so you need to, outside versus inside. In our first example, this was outside the parentheses, right? It wasn't being part of the square. This one's inside the parentheses, so it's part of the cubing process. It's part of that function that's being done. It moves to the left 3. Right, so this one is left 3. So here, when it was plus, it was up. Here, it would make sense to have plus be to the right, but it's not really doing that. It's going the opposite way. Let's see if it holds true. X minus 4. So let's see. I'll do f of x equals x minus 4 cubed minus 4. So where'd it go? Oh, it's down 4, but it's to the right 4. So let's say I took this plus 4 off. When I subtract 4, it moves to the right 4. And then it's still true that if I subtract 4, it moves down 4. And so this one goes down 4, right 4. Let's see if it works with pi. So f of x is equal to x plus, can I get pi here? Hold on, let me see. Pi, here we go. And then cubed here. So where's this point? Well, this is at negative pi 0, so it moved over to the left pi. So I was adding pi, and it moved it to the left. Well, that means that this is left pi. Okay? So the difference between placing the information inside the parentheses and outside the parentheses is which way does it go. And what we're looking at is this. Horizontal translations adhere to these rules. Y equals f of So I'm trying to move to the right c units. X minus c, so inside the parentheses, moves it right c units. Y equals f of x plus c moves it left. So if it's inside the parentheses, plus means left, minus means right. Vertical translations would be f of x plus c moves it up c units, and f of x minus c would move it down c units, okay? And so when we practice this, let's check it out. Describe how the graph y equals absolute value of x can be transformed into the graph of the given equation. Check using decimals. That's that graphing calculator. So let's just look at this. The function is f of x is absolute value of x. So this minus 4 is outside. Does that move it up, down, left, or right? Well, that moves it down 4. Okay, you can pause and try these. If it's inside the parentheses, then it's minus 2. That's going to move it right 2. Okay, because it's inside the parentheses, so inside is opposite. So what we're going to do now is we're going to write 3 functions using given translations, and the first one is the parent function is y equals x cubed, and I want a vertical translation up 3 units. So I got to think, is that inside parentheses or outside parentheses? Is it opposite or not? Well, if I'm going up 3 units, this is plus 3 outside. So my function is y equals x cubed plus 3. That moves it up 3 units. Y equals x cubed is the parent function, and I want to go left 2 units. So this is plus 2 inside. So y equals x plus 2 cubed. X cubed is the parent function, so x plus 2 would be left 2. Horizontal translation right would mean minus 3 inside. So y equals x minus 3 cubed. Okay? Inside versus outside. Outside is up and down, inside is left and right, and it's opposite. Okay, here we go. Let's explore a little bit more. Here I'm putting in negative places. So my parent function is x cubed, so let's hop back over here. I'm going to clear these out. Boom, boom, boom. And it wants me to graph 3 different functions. So I'm going to do this. Hold on, I'm going to get smart here. So it wants me to do a negative x cubed. So a negative x cubed. Well, that's interesting. Look at that. Then it wants me to do a negative x cubed. Then it wants me to do a negative x cubed. Oops. Let's look at them one at a time. Here's my parent function. If I put a negative outside, that, what does it seem to do? Well, it seems to rotate it, right? So, or flip it. It seems to flip it over the y-axis. Right? It seems to flip it over the y-axis. But wait a minute. It could be a flip over the x-axis. Let's look at the next one. See if we can get any patterns here. For this one, it looks the same. So it seems to flip it over x or y. So something's going on here. Something's going on here. When I do both of them, check out what happens. I get my original. Well, how is this possible? I get my original. So that one would mean that I took one, I flipped it, and I flipped it again. So it's the same as the original. Let's look at something real quick. What if I change this to x squared? Let's just check it out for a second. Turn these off. And let's look at squared, because sometimes in math, when you examine one example, you can't really tell. So it's not enough evidence. So let's look at x squared. You're familiar with this one, the squared function, right? What if I did that same thing, and I'm trying to figure out, does it flip it over y, or does it flip it over x? So let's check it out. So when I put an x, so when I put a negative in front of the function, so negative f of x, it doesn't flip it over y. It actually flips it over x. When I put the negative inside, I get the same. So if I was debating, does it flip it over y or does it flip it over x? I would have to say that for this one, it flips it over x. Sorry, over y. How do you know? Well, with the squaring function, you flip it on itself, it's the same. Let's see this next one. For the cubing function, it was the same. For this one, it is the same. So that would mean that it flips it and flips it again, or something else is going on here. Well, the gist of it is this. When we try to work with reflections, we've got three basic rules. To flip across the x-axis, x squared is the squaring function is a good one to look at. To flip across the x-axis, it looks like this. Y equals negative f of x. To flip across the y-axis, we're going to put the negative inside. Now this should look familiar because I am doing the same kinds of things, inside versus outside, as I was doing in the previous examples where I was moving left and right. To flip across the origin, that's the other way. So we've talked about y-axis symmetry, x-axis symmetry. Now we're talking about origin symmetry. To reflect across the origin is actually to do both. Negative f of negative x. Okay, so negative f of negative x will give me both things that I need. It will flip across x and it will flip across y. It will do both of those things. Okay, so it's actually flipping it all the way around. All right, so when I do this, and I do it graphically, it makes some sense. Sometimes the algebraic gets a little bit tricky. And so what they want me to do here is find the equation for the reflection of f of x across each axis. So for the x-axis, they want me to do negative f of x. And for the y-axis, they want me to do f of negative x. Well, it's really just a matter of either multiplying the whole thing by a negative or putting in a negative for the x. So here we go, x-axis would be negative f of x. So it's literally negative times 5x minus 9 over x squared plus 3. And if I do that and I distribute in, it would be negative 5x plus 9 over x squared plus 3. Done. For the y-axis, I need to do f of negative x. And so I'm literally going to put in negative x for every single x. So it's 5 times negative x minus 9 over negative x squared plus 3. So I have negative 5x minus 9 over x squared, because squaring a negative x would just give me x squared plus 3. Well, check it out. What's the difference here? The difference is that I've got a plus 9 here and a minus 9 here. They are different, okay? Slightly, but they are different, and it's significant. Go ahead and pause here. Try this next one. So you're going to evaluate negative f of x and f of negative x. When you come back after the pause, I'm going to show you and do it with you. Okay, so the x-axis would be negative f of x. So it would be literally negative times x cubed minus 5x squared plus minus 3x. Jumping ahead of myself here. Minus 3x. Plus 2, and so when I distribute it in, I've got negative x cubed plus 5x squared plus 3x minus 2. Okay, so that's just negative, so making the function negative. For my y-axis, it's going to be f of negative x. So I'm literally going to plug in negative x for every single value, and so I've got negative x cubed minus 5x negative x squared. Making it all messy, I'm sorry. Negative 5 times negative x squared minus 3 times negative x plus 2. So I've got negative x cubed. Now notice, It's a negative x cubed. So x cubed is negative. And this one would be minus 5x squared, so that doesn't change. And this would be plus 3x plus 2. Okay, so notice the difference here. I've got a positive and a negative there, and the 2 is also different. I've got negative 2 and a plus 2. It's significant. Slight change, but significant. Horizontal stretches or shrinks. So what we can do is we can take a graph and we can smush it, or we can stretch it, or we can smush it vertically or stretch it vertically. And so the way that we do this is it looks like this. So f of x over c, this is the equation for a horizontal stretch. So let me show you. It's a stretch if c is greater than 1. It's a shrink c is less than 1. You're going to see how this works. For a vertical stretch, so you're thinking, well, that looks weird, but literally what you put in is x over the number that you're stretching or shrinking by horizontally. Vertical looks like this. F of x is equal to c times f of x. Okay, so it's literally multiplying the whole thing by a number. And it's a stretch if c is greater than 1. And it's a shrink if c is less than 1. So if I've got a curve be defined by f of x as x cubed minus 16, find equations for the following non-rigid transformations of C1. It's a vertical, so C2, so I'm finding C2. So I'm saying I start out with this parent function, not a parent function, but the original function of x cubed minus 16x is C1. C2 is the transformation. So I want to vertically stretch it by a factor of 3. Well, stretching by a factor of 3 literally means 3 times C1. How did I know that? Well, if it's a vertical stretch, then it's C, so my constant, whatever that is, the factor of 3 in this case, is 3. So 3 times C1. Well, if C1 is x cubed minus 16x, then I literally do 3 times that. So it's equal to 3x cubed minus 48x. Okay, that's literally what my function would be then. So that's my answer. Boom. Vertical stretch by a factor of 3. A horizontal shrink by a factor of a half means that's what I'm dividing by. Look, my horizontal factor goes on the bottom. So watch this. You're going to be like, what? So f of x over c is equal to f of x over 1/2, because that's my factor that I'm stretching or shrinking by. Well, you have to know a little bit about fraction operations. When I divide by a fraction, it's the same as multiplying by the reciprocal. So dividing by a half is the same as multiplying by 2. So to find this horizontal shrink, I literally need to put in 2x into my function. So here we go. 2x cubed minus 16 times 2x. So for horizontal, you have to do a little bit of pre-work first to figure out what am I actually going to be putting in, then evaluate the function. So this would be 8x cubed, because it's 2x times 2x times 2x. You don't just cube the x. 8x cubed minus 32x. Okay, so see the difference there. See the difference there. This is the very last example. The graph of x squared undergoes the following transformations in order. Find the equation of the graph that results. So we're going to do it this way first. So 1, 2, 3, and then we're going to go 3, 2, 1. We're going to go in that order. So 2 to the right would be minus 2 inside my parentheses. Vertical stretch would be 3 times f of x, right? So on the outside. Vertical translation would be plus 5 outside. So here we go. I'm going to start with x squared, so y equals x squared. My first translation is a minus 2 inside, so I'm going to do x minus 2 squared. That's this one. So we did that one. My next translation is to do 3 times x minus 2 squared. I did that one. And then to move it 5 up would be 3 times x minus 2 squared plus 5. And so my result is this. So it's 3 times, and then x minus 2 squared would be x squared minus 4x plus 4, and then plus 5. So I've got 3x squared minus 12x. Plus 12 plus 5 will be plus 17. Okay? I'm doing that to show you that when you expand it, it's going to be different. Let's do them in the reverse order. Okay, so y equals x squared. What if I translate it 5 units up first? So my first translation would be x squared plus 5. My next translation, so that would be this third one here. The second one would be a vertical stretch by a factor of 3. So I'd have 3, hello, computer is freezing, 3 times x squared plus 5. And a horizontal shift 2 units to the right would still be inside the parentheses, not these parentheses, but inside the little function, the little parent function here. So 3 times x minus 2 squared plus 5. So let's see what happens. Literally 3 times. And this would be x squared minus 4x minus, or plus 4 plus 5. So this would be 3 times x squared minus 4x plus 9. So it's going to be 3x squared minus 12x plus 27. Look at the difference here. There's a difference of 10 units. So everything else is the same. But one of them would only be 17 units up. The other one will be 27 units up. Okay, so order is important. Make sure you know what order they're asking you to do the translations in. All right, guys, that was a double section. That was 2 sections, parent functions and also translations of those functions. Thanks for watching, and we'll see you next time.